Hi, so I'm here to talk about hash tables for use in like
Listen
computers.
up, please.
Just like the theory behind hash tables rather than the specific implementation of them. They're pretty easy to use without knowing what's going on behind the scenes, so I'm talking about like how they actually work and what their efficiency is. So what is a hash table? So hash table is basically just an enhanced form of the dictionary. You have a key of any data type, usually a string when we're talking about hash tables being the most efficient, and then just a value associated with that key. So we have our key value pairs, and there's something called a hash function that serves as the middleman between these two that maps these keys to an integer value in the array that has its own unique value that can be referenced like calling any number in an array. So this gives us a more robust version of for searching for specific data. It's unordered, but we can just call up a specific index, work backwards from our hash function to figure out what the key would be, and then grab that value. So in terms of the big O notation, ideally, without dealing with reality, which we'll talk about later, I mean, there's some complications. It's a constant lookup times. It doesn't matter how big the size of the hash table is. Looking up will always theoretically be an O one time. So let's go over some of the pros and cons of using a hash table. So every data structure has its own advantages and disadvantages. And for data set size, a hash table works better with very, very large sets of data. It's definitely the go-to in big databases. So if you wanted a phone book of everyone in Pottstown, a hash table would probably be the best option because you're looking at like 10,000, 20,000 entries. For smaller data sets, there are easier ones such as like dictionary, just array to use that will be faster to look stuff up. For searching algorithms, hash tables are definitely by and far like the best to use because it's basically like searching an array. For big data sets, this is definitely the fastest way to do it. For smaller data sets, you can stick to dictionaries, but definitely the best for bigger ones. Sorting a hash table is pretty much unnecessary because you will always know where to find whatever you need by using the hash function. And expansion, hash tables are an array basically, so they're of a fixed size. It's possible to expand them in a similar manner that we expand arrays, but this isn't as efficient as robust data structures like array lists and linked lists. So let's talk about the actual hashing algorithm. There are many ways to hash a data type into an integer, but one of the most common ones is used to hash a string into an integer. So this works in much the same way as decimal expansion. So like take the number, I don't know, 597. So 597 can be broken up into its base 10 constituents by 5 times 10 squared plus 9 times 10 to the first plus 7 times 10 to the 0. In a similar manner, this is how we turn a string into a unique integer. So we come up with a base for the number of possibilities we need. So for this example that I have up here, I just use 27 because we're just going through uppercase A through Z. Everything can be shifted to uppercase and the space character. If we needed numbers, we'd go 0 to 9 would be 37. It really doesn't matter. It just depends on what you need for your own specific uses. So then you go through your string right here. So right now I have Andy. And then you multiply, you just do a simple, like a decimal expansion using the ASCII values. So A is 65, N is 78, D is 68, and Y is 89. So then you get this one unique integer. And you're guaranteed that this is a unique integer representing my name because you've gone through the decimal expansion process. So part two, the hashing algorithm. So we have a unique number for each string now that we can use to index an array, but the problem is that this is much too big. We would have to create an array with 1,338,182 slots to even get to a 4-letter word. And as the keys get bigger, this gets exponentially larger. So we would need something of this order of 2 to like the 32 is the possibilities for a hash table, or like the entries in a hash table. So we need to map these raw hash values into something that we can use. And the most helpful way to do this is the modulus function. So the formula of that is usually used to hash the raw values down is the array index equals the hash value mod of the array size, so the amount of items you want to store. And this will guarantee that you will have a value that is within your bounds, but this also results in a loss of individuality in some cases, which brings up the reality problem with hash tables, which is collisions. So a collision happens when two keys are hashed and then mapped to the same index. So as you can see here in the picture, John Smith and Sandra D have gone through the hash function and have been mapped both to position 152. And it's cut off a little bit, sorry. But
Damn it, John.
So there are two techniques with dealing with collisions. One of them, the first one is called linear probing, which is a technique that is used. So when you come up to an existing, so let's say John Smith was here first, and Sandra D was hashed at the same position. This is an example of linear probing because it's just moved up to the next available slot. So this is it's usable, but that means every time you call like an array index, you're not guaranteed that that's going to be what you find there. So you have to search like locally within the hash table. And furthermore, if there are multiple collisions in the same spot, then you have to keep going down the table. That messes up other entries that should be there. So it gets exponentially harder to use as the collision rate increases. Collisions are very infrequent usually because the data set is usually pretty spread out over a large range of numbers, but with concentrated data sets, it's pretty hard to use. And the second one is called separate chaining, which instead of storing the, am I going too long? This is a problem. Okay. The second one is separate chaining, which is instead of storing the data type of each array, you store the linked list at every entry point, and then every time there's a collision, you just add to the linked list at that index. So you're searching a linked list rather than searching like an individual value. So that increases lookup time just a little bit, but it's a constant because you just search the same linked list every time. Here's an example of both. I'll look at the diagram. So you see for linear probing, Andrew Wilson just gets moved on to the next slot, whereas in separate chaining, Jack Williams and Andrew Wilson are in the same linked list. Lastly, there's something called the load factor in a hash table. This is like the key statistic for determining how efficient it's going to be. The load factor is defined by the number of buckets, which is the number of available slots in the array. Or no, I had this backwards. Sorry, this is wrong. Number of entries in the array, which is like the number of actual data is like entities stored in, divided by the number of buckets, which is the number of slots. You're going to need more buckets than slots, obviously, because you are going to run into collisions. And you need extra slots in case you need extra slots to move things around to get around this kind of thing. So as the load factor approaches 1, the table will slow down and eventually crash when it has nowhere to put extra collisions. But as the load factor decreases, the less collisions occur, but then you have more overhead and storage costs because you have a lot of unused data. So the default load factor in Java is 0.75, but this can be manually set in your constructor. And the table will automatically resize whenever the load factor surpasses the upper bound, which is usually 0.75.
Yay!